Okay, let's start. So I just have some announcement about the quiz. So I actually don't know what's the interface of uploading your quiz assignment. When I check the configuration in the setting page, there is no option to send notification for every single student. So what we decided to do is that I will ask the TA to generate a list of the submission after the deadline, and then we will announce that summary. So please go to check this the summary. If you didn't see your name on the list, then probably you didn't upload successfully. So just try to re-upload this probably by half day after the deadline. All right. So today we're going to talk about what is modulation. So I think last week we talked about some basic physical layer properties and characteristics. Let's just do some recall. We do lots of math. There are lots of equations. It looks like very scary, but all you have to know is that basically the signal is electromagnetic signal, which is basically very similar to some sine wave or cosine wave. But this is the high frequency signal. You can actually not generate this, for example, 5 gigahertz signal using your computer, right? So to avoid this high frequency signal generation, what we do is that we try to generate the baseband signal, which is operating over 0 hertz, which means there is no center frequency. And basically what you send is just nothing but A plus BI, which is a complex number. So we said that if you can generate this kind of A plus BI signal, it's still discrete, okay? It's a discrete value. So once you have this A plus BI, you can just send this A over a cosine wave on a high frequency band. And then you transmit B using the same wave in a high frequency band. So when we transmit this A plus BI using this cosine and sine wave, we say this is up converter because we convert the 0 hertz signal up to the actual signal we are using, for example, like 5 gigahertz. And then after this up conversion, we say this cosine and sine signal will be the passband signal. Okay, so this is a very quick summary. So as I said, if you really don't know what's the theory behind this conversion, at least what you have to know is that basically the physical layer signal is just a complex number A plus BI. And it's equivalent to something alpha multiplied by e to minus 2j pi ft. So they are actually equivalent, but just this one is the passband signal, and this one is the passband signal carried over this frequency, the center frequency, the actual center frequency. And this is the amplitude. And this is probably some phase delay. Okay, and last time we also said there is a very important diagram called constellation diagram. So this is the real number, this is the image number. So once you transmit A plus BI, it actually means that you transmit image real number A and the image number B. So this vector is actually what you send. So there are two very important properties on top of this diagram. The first thing is that the amplitude squared will be the power of the signal, and the angle of this vector will be the phase delay of the signal. Right? So very quick recap for the vector in the last week. So now the question is, we know that our computer, our device, we are in the digital world. when we are saying we are in the digital world, that means what we are generating is something 0101 bit, right? So that's the digital world. So this is what we generate in the MAC layer. But going to physical layer, you try to transmit A plus BI, which is not 0101 binary string, right? So you need to have some way to convert your message, to convert your information, your binary information, to the corresponding physical complex value. So again, you have application. The application is generating the binary bit string. But the physical layer, we can only deliver A plus BI, right? So you need to have some conversion to convert the binary string back to A plus BI, all right? So this process is what we call modulation. Modulation means that you want to convert a sequence of bits to a sequence of A plus BI, such that our RF chip, our transceiver, can deliver those A plus BI over the air, right? So from the Wikipedia, you can say that modulation is just the process of changing one or more property of the periodical waveform such that we can modulate the signal using the typical cosine wave, right? So here is some visual example. So imagine that we have electromagnetic signal, magnetic wave, which is a sine wave or cosine wave. But there is no information on top of this sine wave, right? So you need to change this waveform. You need to introduce some variation to hide your bit information using this waveform. So when we say hide, you can also say we want to embed some information. 我们想要嵌入一些资讯。We want to embed some information in this waveform, right? Such that you can infer what's the bit information from those changing waveform. So this process is what we call modulation. Modulate. You want to modulate your signal on top of the sine wave or cosine wave. Right. So this is the process for modulation and demodulation. So in communications, remember all the processes. Usually we will have forwarding direction and also the reversing direction. For example, if you modulate data from the original sine wave to this changing waveform, this process is what we call modulation. So this is the forwarding direction. So once you have forwarding direction, then everything you can find the corresponding reversing direction, which means that you want to convert this signal back to the original signal, original bit pattern, right? This process is what we call demodulation. So usually if you see this prefix D, it means the backward direction. And this is the forward direction. All right. So now we will use this M to describe the message we are trying to send. For example, if we were to try to send 010011, okay? So for example, this information, this message can be represented by a bit string, like B1 is equal to 0, B2 is 1, B3 is 0, 0, and B4 is 0. Okay, so this is the bit string we try to deliver to the receiver. And then for the transmitter, you have to do modulation, trying to map this bit pattern to some actual signal. Here we mean this is baseband signal, which is actually A plus BI, as we introduced in the physical basics lecture. All right, so what we want to do is we want to convert this bit string to some A plus BI. Okay, so now here is the question. Can we convert long sequence of the bits to just one single A plus BI? Can we do that? Or can we just convert, for example, 2 bits to A plus BI, or maybe convert 4 bits to A plus BI? So that's the question. So the answer is either way is fine, but there is no optimal choice. You have to decide how many bits you want to convert to one A plus BI at a time. OK， 所以 modulation 呢是说你要把一组 bit pattern 转成 A plus BI， 用一个 A plus BI 来表示。那问题就是说你到底要把一长串的 bit 对应到一个 A plus BI， 还是把比方2个 bit 对到一个 A plus BI， 还是把4个 bit 对到一个 A plus BI？ 其实都可以，可是这会取决于你的通道的品质的好坏。那这个我们下一堂课会讲。Alright, so basically you need to give a number of bits. For example, let's say k bits. This is a predefined number. So we want to represent this k bit using a single A plus BI. That is what we mean by modulation. And then you will transmit this A plus BI over the air to the receiver. And remember, when you are using a wireless channel, usually we will see some noise. Remember, last week we said we should calculate the SNR, which means the signal to the noise ratio. You have to compare what's your receiving power to the noise you receive, right? So there is no perfect channel. There is no perfect wireless link. Whenever you deliver something to the air, you will see some noise. So basically, this XS is nothing but just some function of what you are delivering and plus some noise. Which means that what we receive at the receiver, of course, is different from what you are transmitting. Okay, so you need to have some reverse processing to convert this received signal. This is probably A prime plus B prime I. Basically, it's a different complex number as compared to A plus BI. Basically, it's similar to A plus BI, but just with some delta. So you can imagine that this A prime plus B prime I will be something like A plus BI plus some small delta, small noise. Right? So given this A prime plus B prime I, you have to convert this complex number back to the bit stream such that we can recover the original bit stream. So this process is what we call demodulation. All right, but it's not so simple, right? Because remember, this is not perfect. This is not exactly A plus BI, right? Because we have some noise here. So if you have some noise here, when you do demodulation, when you convert this back to the bit pattern, you probably will see some errors such that the converted bit pattern probably will become different from what you are trying to transmit. In that case, we say this is demodulation error. So for example, if you are delivering 10100, if your demodulation give you 0100, then that's perfect. You're fine. Even if you have some small delta here, that's fine because you still get what you want, 0100. But if, unfortunately, if you are trying to deliver 0100, but if this delta is too large, such that when you are doing demodulation, you probably will get 0110, which doesn't match the original bit pattern, right? So this is what we call by demodulation error. And in this case, we only have one bit error here because only the third bit is flipped from 0 to 1. So there is only one single bit error. But it's also possible that when you are doing demodulation, you get something like 0010, right? Then in this case, we say there are 2-bit error because the second bit and third bits, they are all in error. Right, so that's the demodulation error. Right, so that's the whole process. So let's read through the description one by one again. So modulation means that you want to encode a bit string. Basically, this is what we mean by N. And remember, this is the finite length of the bit string first. For example, in this case, we are converting k bits. And usually this k is fixed. And then we want to encode a bit string to one of several possible signals. This is very important. So we haven't described what is one of several possible signals. Several possible signals means that you have a predefined set of a plus bi. For example, we have 0 plus 0i. No, this is not good. 1 plus 0i, 0 plus 1i, 1 minus 1i, 1 minus 1i, minus 1 plus 1i. For example, you can predefine a set of complex numbers. All right, so this is predefined. For example, if you have 4 choices, if you have 4 options, then what is the k? K can be 2, right? Because if k is 2, that means we can have 0, 0, 0, 1, 1, 0, or 1, 1, right? So if you have 4 patterns, you can actually embed 2 bits, right? If you have one-to-one mapping, you can say, okay, if my bit pattern is 0, 0, then I try to transmit 1 plus 0i. If my bit pattern is 0, 1, then I can transmit 0 plus 1i. Ouch. Sorry. And then if you are delivering 1, 0 bit patterns, you can transmit 1 minus 1i, for example. So this is what we mean by one of several these possible signals, because you have to predefine a fixed set of the signals of the A plus BI such that you can do one-to-one mapping for modulation. So basically, modulation is very simple. It's just some one-to-one mapping. You don't really need a very complex function to do this conversion. It's just a very simple one-to-one mapping. Right. Let me drop this. And then once you get your A plus BI, for example, let's assume we are transmitting 1 plus 1i, and go over the airs, you might receive some noise, and then the signal and then the noise will combine together, become the received signal X. And then given this received signal, you try to convert this signal back to the bit pattern. And remember, from the previous example, we said our possible set of the complex number, for example, is 1 plus 0i, 0 plus 1i, 1 plus 1i, 1 minus 1i, for example. If we have this 4 pattern, then given the received pattern probably is something like 0.9 plus 0.8i. So actually there is no this option in this set, right? If we can have perfect reception, of course you can say if we receive 1 plus 0i, we say okay, this is 0, 0. If we receive perfect 0 plus 1i, we say this is 0, 1, right? But what we are receiving is actually the signal with some noise. So how can you know that what you are receiving is the first one or the second one or the third pattern or the fourth pattern, right? So you need to have some way to infer, to guess, okay, I received 0.9 plus 0.8i, probably this is the third one. So this guessing process is basically the bit modulation, right? If you guess correctly, then you can easily convert it, say, okay, this probably is the third one, so what you are delivering is 0, 1, 0. So that's the demodulation. So basically, you want to decode the received signal, the decode noisy signal, by mapping it to the most similar pattern. When we say most similar, which means that we have some predefined patterns here, we want to infer which one should be what you want to transmit. If you can infer correctly, of course, you can convert back to the correct bit pattern. All right, so this is demodulation. Any questions so far? Okay, so that's the very quick overview of the whole process. So this is the other diagram. I should try to modify these notations because the notation is a little bit inconsistent. Let's keep this as in. Let's keep this as S. And you do some power allocation AS. And then because you might also have some channel response, remember we said channel response is nothing but just the variation of the amplitude and also some phase delay, right? So you will receive some phase delay and amplitude variation on top of what you are transmitting, and then you also get some noise. So all this H and N will introduce some variation on top of your signal. So there is also one process called equalization. Let's skip this. Basically, you need to guess what is the edge, and then such that you can remove this edge. But we will introduce this next week. And assume you can remove this edge, then basically you will get something like real S plus some delta. Okay, we say this is S prime. So the demodulation means that you want to convert this S prime back to some bit patterns, and hopefully we hope that this bit pattern can be exactly the same with this one. But in this example, you can see that this bit is flipped, right? So there is one big error. All right, so this is modulation and demodulation. And so now we have already seen the quick overview. So let's go into some more details about what are the different modulation algorithms. So modulation is just a general terminology representing that you try to convert a bit patterns to some A plus BI. But how to convert, how to do this conversion? If there are actually many different algorithms, you can have different way to represent your bit pattern, right? Because when we go back to here, we say, what we have is a sine wave. You can embed your information in any way you like, right? For example, if you want to write some secret to your friend, you can just define your own secret key. You can define your own pattern to hide your information, right? There is no single solution. For example, if you want to hide a secret like I love you, different couples can have different way to hide their information, right? You can imagine that just using different secret, different messages to hide your information. So when we're using different information or different way to embed your information, that means we will use different modulation algorithms. All right. So our goal is to convert bitstream to some A plus BI, but you can use any algorithms you like to do this embedding. So this is what we call by modulation algorithm. So if we classify the modulation algorithms into two types, we can say some are doing analog modulation, some are doing digital modulation. So analog modulations means that your signal variation is applied continuous. So you can see that this variation is changing over time without any boundary. This is continuous changing. So this is what we mean by analog. So if you see some term analog and digital, it actually means this is the continuous changing, and digital is equivalent to discrete. Okay, when you say digital, that means you want to do decision one by one by one. But if you see analog, means that this decision can changing over time continuously without the boundary. So one is the continuous changing, one is discrete changing. So for analog modulation means that you can change in this waveform continuously. Okay, and some very famous example is AM and FM. So if you have listened to the radio on a car, you will see that the radio program sometimes some are from the AM channel, some are from the FM channel, which means that the radio program when you are driving, it's actually modulated using analog modulation. Okay, so those audio sound, they are modulated using analog modulation. All right, but in digital communications, why we are saying digital communications for wireless communications sometimes? Because our information is delivered using the digital modulation. So this is why we usually say we are doing digital communication. So digital communication doesn't mean that we don't use sine wave, cosine wave, but just saying we are using this digital modulation. Okay, so when we say digital modulation, this means that this is a discrete modulation. You can see there is a very clear boundary for every single pattern here, which means that you will chunk the time slot into several intervals. And for each interval, you just apply a modulation scheme once for the whole interval. All right, so you can see that here we decide to transmit some sine wave, and if this is 0, we decide to transmit nothing, right? So you make decision for every single interval with this boundary, predefined boundary. So this is what we call by digital modulation. So this is what we say, this is different from the analog modulation, because the analog modulation, you cannot see the clear boundary, you are changing over time. All right, so the most famous algorithms for digital modulation will be ASK, FSK, PSK. A means amplitude, which means you try to change the amplitude of the signal. And F means FSK, frequency, which means that you try to hide information using frequency. And phase shift key means that you want to hide the bit pattern using phase information. And there is also something called OK, which means the on-off keying, and also some other example PPM. So there are so many different algorithms. You can just search Wikipedia. They will give a full list of all possible algorithms. But in our class, we will just introduce the most common algorithms, which is ASK, FSK, and PSK. All right. Any questions so far? All right. So here is the slide telling you what's the advantages of digital modulation. Yeah, there are some benefits. Otherwise, we will just use the analog modulation, because analog modulation is the older algorithm. So the newer algorithm will be digital modulation. So the good thing is that digital modulation, they can give you a higher data rate. Assume that we have a fixed bandwidth, assuming that our bandwidth is 220 megahertz. Remember last week we said there is one theory called Shannon capacity, right? The Shannon capacity is a function of the bandwidth multiplied by the log 1 plus S and R, which means that the larger bandwidth you are using, of course, the higher capacity you can achieve. But now if you have a fixed bandwidth, if you are using digital modulation, it actually can give you a higher data rate. And the second advantage is that it's much more robust. When we say a modulation algorithm is more robust, what does it mean? It means that if you have some message, you convert this to some A plus BI signal, and then add some noise here and become S prime and becomes N prime. Assuming that this delta is a constant, the modulation algorithm is more robust if the probability we can get M prime equal to N is higher, then we say this algorithm is more robust, right? Because you can have a higher chance to decode the bit pattern you are transmitting, right? Which means that the successful ratio is higher. So if this probability is higher, then we say this modulation is much more reliable. 好 ，reliable 意思就是说你在你的 channel 会给你这个 data， 给你这个 noise 的时候，并不是所有的演算法在做 demodulation 的时候，它都会得到同一个 m prompt。通常不同的演算法就会得到不同的 m prompt。所以我们说有一些演算法如果给你的 m prompt 有比较高的机会可以等于 m， 那是不是就是我们要的嘛？对不对？我们当然希望 m prompt 等于 m 啊。你总不希望我今天送了一个讯息，结果收到是另外一个嘛，对不对？好，所以如果你的 modulation scheme 给你的 m prompt 可以有比较高的几率等于 m 的话，那我们就说这个演算法是好的，因为它比较可靠，哦，你就不会误会它的意思嘛。OK， alright. And also, it's more suitable for multiple access, which means that if you have multiple users who want to transmit simultaneously, it's actually better to do digital modulation because you have a clear boundary. And then you can say, okay, everybody just try to start transmission in the beginning of the boundary. And it's also secure and private. If I'm not doing security, but for the security, if you want to do some encryption, it's easier if you can encrypt on top of a discrete signal. All right, so there are, of course, several theory and mathematical proof to prove, okay, digital modulation actually can perform much better than analog modulation, but we will not give you those proof, okay? You just need to remember this is the benefit of the digital modulation. Okay, so now we know what's the difference between analog and digital modulation. We also know the benefit of digital modulation. So from now on, we are going to introduce several very important digital modulation algorithms to you. So actually, there are like 4 or 3 important algorithms you should learn if you really want to know what's the Wi-Fi transmission or what's the 5G communications. Okay, and there is no actually big theory behind those modulations. Even if you are a kindergarten kids, you can actually hide your information, even if I don't give you any theory, even if you don't read any textbook. Okay, why? If you see this figure, now assuming you are a receiver, if you receive this pattern, can you guess what is transmitted by the sender? I guess you have answered, right? Because it looks very intuitive. 你觉得这个会是 sender 会送什么？ Okay, let me give you the option. Sorry, I forgot to press the button key. So if I give you some choices, A or B or C, 所以你猜猜他大概会在送什么 ？B, OK。所以觉得是 A 的举手，觉得是 B 的举手，觉得是 C 的举手。OK， 大家都猜对。OK, everybody is correct. I don't even teach you what is the modulation algorithm, right? I don't teach anything. So you just see this figure, you know what's the answer, right? Because it's very intuitive. Because we are human beings, we have visual effect. So if you have visual effect, you can clearly see that this is. Let me change the color. This is clearly the boundary of the signal, right? If we assume that the interval of each, if the duration of each interval is the same, then we should have this clear boundary for this signal, right? And then we can see actually there is only 2 patterns in this figure. There is only low, low, and high, and low, high, low, high, low. So we can say, okay, this is low amplitude, high, low, high, low, high, low. Then if we say we try to embed bit pattern 0 to this low pattern, we want to embed bit 1 to high pattern. Then we can easily get this is 0, 0, 1, 0, 1, 0, 1, 0, right? So even if I don't give you this conversion mapping, you can still infer this bit pattern probably will be 0, 0, 1, 0 by 0, 1, 0. Or alternatively, we can also say, okay, now I want to hide one bit 1 to low pattern. I want to hide bit 0 to high pattern. That's also fine. We can also say, okay, this is probably 1, 1, 0, 1, 0, 1, 0, 1. So either way is fine. But you need to negotiate between the transmitter and the receiver. If we can have some initial negotiation between the transmitter and receiver, if I'm saying, okay, I want to use this conversion. If you also know that, then when you do demodulation, you can easily convert L back to 1, right? You will easily get, okay, because we are having our negotiation using this kind of conversion. So given this pattern, I can easily convert my signal back pattern back to the digital bits. Okay, so that's the very clear example. So similarly, we said this is one way to hide your information. But you can also hide your information using any different way, right? Because I say, given a fixed messages, you can have different way to hide your information. So for example, in this figure, can anybody guess what's the parameter I'm using to change my signal? 带着我这个讯号是用什么 parameter 来去藏我的讯号？有人知道吗？有没有举手一下？ Okay. Indeed, yes. We are using the frequency of our sine wave or cosine wave to represent our signal, right? 所以 modulation 基本上就是很像你们在玩大地游戏，在藏一些小问题一样嘛。在关主就藏了一些东西，即便我不告诉你这些小资讯，你就看一看，就大概觉得，他就是用某一种东西在藏资料。OK， 这就是 modulation。Okay, so in this example, again, we are using fixed boundary to partition our signal. But just now, we changed the frequency of the signal for each segment. For example, this is the low frequency, we say F1. This is high frequency, we say F2. And this is low frequency, F1, F1, F2, F1, F2, F2. So if we can say F1 means bit 0, if F2 means bit 1, then we can easily infer this is probably 0, 1, 0, 0, 1, 0, 1, like something like this, right? But of course, you can also say, okay, I can also say I want to do the conversion, converting this F1 back to 1, converting F2 back to 0. That's also okay, fine. Just you need to negotiate between the transmitter and receiver. Okay, so the third example is a little bit not so intuitive, but it's still reasonable. We still have some fixed boundary here. Oh, I can't do that. So we still have the fixed interval, but just now we can see that the frequencies, it seems that the frequency is also the same, the amplitude is also the same. But if you see carefully, you can detect that the actual difference is what is the phase. For example, in this interval, we are sending some sine wave, and this is a sine wave. This is actually cosine wave. Cosine wave means that you have some shift for your sine wave, right? So you will get some cosine wave. So the difference between sine wave and cosine wave is nothing but just some phase delay. And this is also sine wave, cosine wave, sine wave, cosine wave. Yeah, and cosine wave. All right. So you can see that if your phase has no delay, and also if your phase have some 90-degree delay, then we say this is mapped to bit 0, this is mapped to bit 1, right? So here is the example. We can also use the phase rotation or phase delay to represent bit 0 or bit 1. Right. So given that, we can also say, okay, by detecting the phase delay, we know you are sending 0 or you are sending 1. So here is just another summary. So modulation basically is trying to map the bits to some complex value or to some sine wave or sine wave signal. And then given this bit pattern 1, 0, 1, 1, 0, you can have some way to generate the signal using any parameter variation you like. And then when we transmit this over the actual channel, actual signal, you might receive some disturbance, some variation, some noise. We say this small variation will be the delta. Okay? And then given this data, we hope that we can still visually see what's the information. For example, in this case, the noise is actually quite small. So even if you add this red signal with some small variation data, you can still see there is a very clear difference between the high amplitude and low amplitude, right? So you can still visually detect this is high, low, high, high, low. So you can still demodulate this back to 1, 0, 1, 1, 0. Right? So we said that the demodulation error is that when you receive the signal with a noise too large, then you probably will convert this received signal back to a wrong bit pattern. Then in that case, you will have demodulation error. So why? Because the received signal may be distorted by the noise, which is too large, such that you cannot infer the signal correctly. So the probability of demodulation error is actually depending on the SNR you have, or the SINR. When we say SINR, the only difference is that originally we say we have the signal power, or this is receiving power, divided by noise threshold, right? We hope that this signal power should be much larger than the noise power, such that we can have a good channel quality to recover our bit stream. So this is the SNR. And the other case is sometimes this noise might be very small, but unfortunately there are some other users sending overtime at the same time. So you will receive some interference. You will receive some interference signal from your neighboring nodes. So your neighboring node is transmitting simultaneously, but their signal is not the signal you want, right? So this is becoming some interference. So usually this interference will much larger than the noise. So of course, if your signal power is comparable to this I, we say the SNR, then this SNR will be very small. In that case, your decoding will usually be failed because the interference power is too large. 好，就是 SNR 跟 SINR 只是差在 SNR 是当你没有干扰的情况下，你就只有 noise， 就是一般机器或是网卡的 noise， 那通常很小很小。那另外一种是 SINR， 就是除了你网卡收到这种机器里面的一些硬体的 noise， 你还会收到干扰，比方说我跟其他人，你的 transmitter 啦，跟另外一个不是你的 transmitter 都同时在送，所以你就会同时收到你要的东西跟莫名其妙外面来的东西会搅在一起。那这个莫名其妙来的东西是你不要的嘛？你不要的东西你就把它放在分母，好。那当你真的要的东西跟你不要的东西，它的 power 能量差不多的时候，你就会发现这个 ratio 就会很接近1嘛，就是根本就分不出来这样。Okay? And this is the first parameter that will determine your error probability, even if you are using the same algorithm. even if you are using the same modulation algorithm. Okay, so if you fix the modulation algorithm, of course, if your SNR is higher, then your success probability will be higher. All right, so this is the first reason that will change the demodulation success probability. The second parameter is actually the modulation algorithms we are using. For different modulation algorithms, we say some are more reliable, some are less reliable. Okay, so that means if you have a fixed SNR, if you have a fixed channel quality, if you have some reliable modulation scheme, then your success probability can be higher. If the modulation scheme is less reliable, then of course your success probability will be lower. All right? So when we want to do comparison, you need to fix all the parameters, but just compare one changing variable, right? So when we want to compare the impact of SNR, you will assume that you use the same modulation scheme, so such that for a fixed modulation scheme, the higher SNR will give you the higher success probability. But now, if you want to compare the performance of different modulation schemes, you should assume that you fix the SNR and to see when you compare algorithm 1 and algorithm 2, which one will give you a higher success probability, right? So we also have some design constraint, because even though we say we can hide our information using any kind of algorithm you like, we still have some constraint. The first constraint is that your bandwidth is fixed, and for example, you can only occupy 20 megabits per second, 20 megahertz, sorry. And you might also have some power limitation. You cannot say, oh, I try to generate a super large power like this, and using this small power to represent 0. No, right? Because for every single hardware, you have some limit power to generate your signal. You cannot say I have some infinity power to deliver my signal, right? You still have some limitation. And then, for example, you also want to say, probably I want to guarantee the minimum possible error probability, right? So if you want to guarantee some minimum error probability, you probably should carefully design your algorithm to guarantee that the error probability is bounded. And also the cost is also very important. When we say cost, sometimes it could be the processing cost, which means the complexity. 你们都修过演算法了吗？ Have you took the algorithm class? 还没修过演算法，举手一下，我要看一下。那要知道 ，so complexity means that how complex is your algorithm. Like, of course, you want to have a very simple algorithms to do the conversion. You can also design an algorithm. For example, you do so many steps or so many different mathematical equations to do your conversion. But this is not what we want, right? Because this converting process is too complex, right? So you still need to care about whether this is an efficient algorithm. And on the other hand, the cost can also be the energy you are using. When we say energy, that means the average power you are delivering your signal, right? Because when you are generating some signal, it's consuming your battery, it's consuming energy, right? So you probably will use the average energy like 10 to deliver your information. But it's also possible you deliver your information using the average energy like 100, right? If you have these two options, of course, we will choose the first one because the energy power is much smaller. It's more energy savvy, right? And some other costs could be the hardware cost, because for those algorithms, it's usually implemented in the hardware instead of the software. So you still need to consider what's the cost of this hardware implementation. 好，所以 cost 可以指很多个不同面向的 cost 啊，这只是一个很笼统的概念。那基本上就是说，我们当然是希望又要快，又要省电，又要便宜，然后又要好。 好做出来了啊，这就是我们所谓的 cost。All right， 忘记删掉 OK， let's finish these 2 slides and then we can take some break. So for a modulation scheme, if we want to write this mathematically, basically what we want to do is given a k-bit string. K is bit, which means the length of the bit string. For example, we want to encode k bit at a time. And then we want to convert these to n possible signal, which means that, as I say, we have a set of a plus bi. Probably this is the first one, a1 plus b1i, or a2 plus b2i. And there are so many options, like a plus bmi. Okay, so remember, we know that if you have k bit, that means you have 2 to the k different bit string, right? So for example, if you have 2 bits, that means you have 2 to the 2 bit pattern, which is 4 bit pattern, right? 0, 0, 0, 1, 1, 0, 1, 1. If you have 3 bits, then that means you have 2 to the 3 bit pattern, which is 8. You have the 0, 0, 0, 0, 0, 1, 0, 1, 0, 1, 0, 0, 0, 1, 1, 1, 0, 1, 1, 0, and 1, 1, 1. Right? If you have 3 bits, you have 8 different patterns. So which means that once you have k bits, you will generate 2 to the k different patterns, which means that you need to have m different patterns, m equals to 2 to the k patterns to represent each of these individual different bit patterns. OK， 好，这蛮重要的哦，这是简单的数学了，我想资工系学生应该知道。你如果要表示 k 个 bit 的话，那是不是就有2的 k 次方种不同的 bit pattern？ 所以你就要去找2的 k 次方种不同的 a 加 bi 去每一个去对应到原本的一个 bit pattern 哦。所以这个 n 是到底要有几种不同的 a 加 bi， 这个 k 是你的 bit pattern 到底有多长 ？OK， so we can say that m, the number of different patterns m should be equal to 2 to the k, or alternatively we can say k should be equal to log 2n. Okay, so these 2 equations, they are equivalent. All right, so what's the data rate? Data rate means that we are doing discrete digital modulations, right? So we are trying to do modulation for every single interval, assuming that this interval duration is t. And then because we hide k bits using a single interval, right? So you can now do some very simple calculation, know that the data rate R will be equal to k divided by t, right? Because you are hiding k bit using a single interval. So the data rate will be k over t, all right? So now you can discover that the more bits we try to hide at a time, then you get a higher data rate, right? So for example, if we have a fixed duration t, now we can say we have an algorithm which can convert 2 bits at a time. And the other algorithm, we can convert 4 bits at a time. Which one will give you a higher data rate? Of course, 4, right? So one is 2 to the t, the other is 4 to the t. So of course, this one has a higher data rate. But you might ask, if this one gives me the higher data rate, why don't we just use the right-hand side solution, right? Why should we use the left-hand side? Anybody knows the answer? 如果我们现在都说了嘛，就是多长一点 bit data rate 就会比较高啊，那少长一点 bit data rate 就比较低嘛，对不对？那如果这样子，那当然是选右边这个啊，为什么要选左边这个？大家不要猜一下为什么？猜不人，猜猜看。 会有问题。好，差不多，有没有更精确的解释？还是他说区分上会有一点问题。什么叫区分上有点问题？如果用我们刚刚讲的专有名词叫什么？比较容易有 error，或是再更数学一点的讲法是什么？用一个比较上过的课的术语叫什么？比较容易有 error。不要看我们中文的，就是 error probability 会比较高嘛。简单讲就是这样。Okay, so basically, why we might choose the left hand side instead of the right hand side? Because in general, the fewer bits you are hiding, the error probability will be smaller. So you cannot just choose the algorithm according to the data array, because the actual information you get will be the data array actually multiplied by your successful ratio, right? This is actually what you get as the receiver, and this is what you deliver from the transmitter. So how many bits you deliver doesn't mean how many bits you receive, right? So R is the data array, which means how many bits you deliver during this T. We still need to double check what's the success probability. You can actually recover those bits, right? So you try to actually recover those bits with some success probability. So the basic idea is that, of course, we want to maximize the data rate multiplied by the actual success probability. This is what we want. So you cannot just say, okay, this algorithm gives me a higher data rate, of course I will choose this one. No, because you still need to see what's the success probability. All right. So yeah, so you need to consider, because you want to do demodulation, so there is some success probability. So once you want to design a modulation algorithm, you need to consider what the data rate you can have and also what's the success probability you can have. So now we already know what is the possible options to design a modulation scheme. So in the previous examples, we said we can change the amplitude, we can change the frequency, we can also change the phase delay, right? So we use these three examples because actually in the spectrum waveform, this is the only three parameters we can use to change the shape of the cosine wave. So one is the amplitude, A here. So you can say I want to multiply by a factor larger than 1, or I want to multiply by a coefficient smaller than 1. This is the amplitude. And you can also change your sending frequency at the transmitter, saying by probably transmitting 2.4 right now and transmit 2.5 next time. And you can also change the delay of the cosine wave, saying that the phase delay should be 0 or 90 degrees. So according to the parameter you are changing, you can say this modulation is the ASK, which means that you hide your information by changing the amplitude. Here you can see this is low amplitude, high amplitude. Or you can say we want to hide our information by changing the frequency. So you can see this is low frequency, high frequency. Or you can hide your information by changing the phase. For example, this is no delay and maybe some delay here. All right. And even more interesting, you can change multiple parameters at a time. For example, you can change amplitude and also the phase at a time. Okay. So this is what we are using this waveform to represent A, SK, F, SK, P, SK. But going back to our constellation diagram, remember we said what we are transmitting is nothing but just some real number and image number. We are sending something like A plus BI, right? So if we try to change the parameter A, F, and phi, we can actually find in some corresponding change using this constellation diagram. All right. When we change A, means that we might using a longer vector to represent 1. And then we might use a shorter vector to represent 0. So this is the low amplitude, and this is the high amplitude. So which means that if you are sending 1 plus 1i, and also if you are sending 0.5 plus 0.5i, their phase is actually the same. Okay, their phase are both by 45 degrees. And their frequency is also the same, just some center frequency, because you cannot see center frequency from this figure. But the only difference is that the amplitude here is higher, the amplitude here is lower. So that is equivalent to ASK. So from the signal point you see in this IQ plane, you can know this is using ASK. Okay? And again, if you are using PSK, that means you might send in some signal here, which is probably 1 plus 1i. And you might transmitting signal here, minus 1 plus 1i. So this is what? This is actually PSK, right? Because for the first signal, it is 45 degrees. For the second signal, it is 135 degrees. So basically, it changes the phase. So if you using this to represent 0, you using this to represent 1, we said this is PSK. But for FSK, you cannot see from this IQ plane. But basically, why we are using this constellation point? Because it is easy for us to represent different modulation scheme on top of this IQ plane. All right, so let's have some break, and then we will continue to introduce what is ASK.
改的时候，有2个人用中文写，有2个人用中文写他的 quiz， 这样我要给他60分，我要给他0分。
哎，我说可以用中文写啊？
没有吧？你不是说 quiz 这样一个？是那个 midterm 的时候才给。
前几次先编好了，我今天在。
我是有想说，我们因为佳瑜明天他要比较忙，他可能比较晚改。那我想说，等改完之后发完，然后之后可能建议大家用英文写。
对啊。
然后可能要上交的时候缴 PDF。
他们不是缴 PDF 哦？
就直接缴 Word。
哦，好，那，因为今天的他们还能交啦，看你要不要今天先就 announce 一下。
好啊。
所以今天以前的就算了，那今天以后就请大家交英文的那个 PDF 这样。
OK。然后